Hello everyone. So last video we talked about how to count the steps in a given piece of code or a given algorithm to derive an equation that captures how many steps it takes to execute that algorithm as a function of the input, right? So we have t of n, and n is some input, some number, the length of a list, something like that, that dictates how long your algorithm runs. Well, in this video, we're going to talk about Big O notation. And Big O is the way of kind of transforming these very specific computations of t and n into a language that gives us an order of magnitude of how good these things are. And that's what the O is in Big O. It's order of magnitude. So like, is your algorithm pretty good? Is it like fast? Is it really fast? Is it really slow? And what do those different categories of things mean? Do you got an amateur algorithm? Do you got a professional algorithm? We're going to try and categorize algorithms according to how big those T of n's were. Okay, so remember, most algorithms runtimes can be expressed as a function of the input size. So the input size is the n here. It's the thing driving the number of steps. And we created T of n's that looked like something like this, 2n plus 2. Okay, now what we're really interested in here is the rate of growth. That's going to be our basis for comparing two algorithms to one another. How fast does this t of n change as you change the n? Right? How fast does it grow? It's a function, right? And when we go to calculus, when we go to trig, we are interested in the slope of functions, right? The derivative of those functions, how the rate of change. That's also what we're interested in computer science. As you change the size of the input, does your algorithm kind of stay the same? Does it suddenly get worse? Does it suddenly get very, very bad? That's what we care about. Okay, so we want to distinguish between fast and slow growing functions. And when we talk about these things, we only care about really big inputs. Right? Computers are fast if you put a stopwatch to them. They can process data quickly. That's their purpose in life and their purpose in creation. So we're really focused not on, input size of 10, input size of 1,000. You got to get up into the tens of thousands or hundreds of thousands to find things that we care about, right? Processing a list of 10,000 numbers or 100,000 names or a million records. Then we start to see some interesting stuff with modern computers, right? Back in the 50s when we had little computers, we did care about tens versus hundreds and things like that. But nowadays, you got to get up into the many of thousands before you really see distinctions in how well algorithms perform. But anyway, data on the scale of thousands, it's everywhere. All right, so growth rate. All right, I've got two functions here, two t of n's for two different algorithms. And they're plotted on the same chart. Okay, we've got t of n is n to the n cubed plus 2n squared. That's the red line here. Okay, and so our x value is n. Okay, 1, 2, 3. That's our x is n. And then t of n is the y-axis. Okay, so n cubed plus 2n squared, that's the red line. 100, ooh, big number, n squared plus 1,000, that's the blue line. Okay, so the blue line is bigger, right? But the question is not which one is necessarily bigger here in this frame, but which one grows faster, right? Why do we care about growth? Because the thing that grows faster is ultimately going to overtake something that grows slower once your n's get big enough, right? So here we're zeroed in on very small values of n down here. Let's zoom out. Okay, how about now? 20, 40, 60, 80, 100, 120. These are bigger values of n's, and look what happens. This red line, at this point, right around here, right around 100, overtakes the blue line, okay? Because the red line grows faster. A function that is n cubed grows faster than a function that is just n. Go back to your trig, go back to your calculus. What's the derivative of n cubed? It's 3n squared, right? So the growth rate is on the order of n squared, whereas the growth rate of 100n squared plus 1000 is on the order of just n. Okay, so that kind of leads us to our big O notation. Now, this is a lot of notation. We say that t of n, a function that characterizes an algorithm using our counting rules, is big O of something. Okay? Big O of f of n. F of n is your typical standard mathematical notation for a mathematical function. Okay, so big T of n is big O. Big O means order of magnitude. It is order of magnitude of some function n of n if there exists positive constants c and n0 such that T of n is going to be less than c times whatever function for all n greater than n0. Okay. We are concerned with how the function grows when n is large. The little additions and subtractions to our t of n doesn't matter then, right? So, for example, kind of what we're saying is, look, this 100 n squared and this plus 1000, it's all kind of noise here on this blue line, because what really matters, this blue line starts out fast, but what really matters is big N's. How fast are you growing? Because blue line starts in the lead, but then it very quickly becomes dominated by red line here. And in fact, blue line, which is order n squared, and will never, ever, ever catch up to the red line, which is order n cubed, simply because n cubed algorithms grow faster than n squared algorithms. Okay, let's look at this graph. Okay, remember, okay, there exists a c times f of n, that's this guy. Here's our t of n, and this is some weird funky function. I don't even know what you would write this equation as, but it doesn't matter really. T of n is the thing you calculated for your algorithm, the steps you computed. And this is what its function looks like. Kind of funky, right? What we're saying is there exists a different function, f of n, okay, such that when you multiply this f of n by a constant c, okay, c is a number, okay, 1, 5, 100, 1,000, something like that. You could figure out what it is. The point is, it exists somewhere. That when you multiply this function, this other function, not your t of n, but some other function, it's either going to be n or n squared or 2 to the n or n cubed, that c times this other function, that there comes a point which is called n0, this guy right here where they cross, where the blue function from that point on is always going to be bigger than your t of n function. Okay? So t of n is less than, it grows no faster than this f of n for bigger values of n. Okay? There comes a point called n0 where your function, the thing you wrote, your algorithm, grows slower than some other function multiplied by a constant. Okay, that's what big O means in graphical form. And maybe this is the easiest way to think about it, right? This crossing point exists, okay, somewhere. It could be on the y-axis itself. It could be over here. That's okay too. Okay. But there are going to be n's and n squares and 2n's or something like that, where your function is always less than that, and that is its order of magnitude. Okay, so let's look at this. Okay, so here's a linear function, big O of y equals n. Let's look at, let's add another one, y equals n squared, right? Looks like a parabola, right? So down here, can we zoom in, right? Now I can move artificially my little y line. Say my y line represents an actual algorithm, 2 of n plus 2. Okay. So it starts out here. Here's my little algorithm. We can always find, there's always going to be a point where this blue line crosses this green line. Okay. And in fact, I can make this about as big as I want. Right? But if I scroll up here far enough or zoom out far enough, I'm going to have to go really far. It isn't the best idea. Let me make this a little smaller. Holy cow. Okay. There's going to come a point where, whew, okay, here it is. Green is the y line, right? At some point up here, where are you? You're way up here somewhere. At some point, this green line gets crossed over by the blue line. It's almost there. I've made these values too big. I've made my life too hard. Let's make it a little less ridiculous. Sorry about that. All right, if we get it down to 200, it's probably a way to get back to the origin. Well, this is exciting. Let's not do this in the actual video. We'll trim this out. And let's just start again. Okay, so let's go over here. Let's plot what we mean. Okay, so we say that there's, let's put a function in here. Y equals 2n plus 3. Okay, so this is, let's say that this belongs to my regular function. You know what? Let's do better than that. Let's go get one of the ones that we used before. We had 3m plus 3 for that sum between function. So here's the t of n line for that. Okay. Let's go in here, and now what we're saying is t of n is big O f of n if we can find an n and a c where we multiply c times this f of n, and from that point onward, the second line is always bigger than the first. Okay, kind of botched that. All right. So the question is y, is my black line, is my first algorithm also big O of n? Well, that implies that we can find a value, a multiplier, for right here that will put this red line above the black line forever. Okay, so let's see if we can find that. What if we pick 3? So you can see that putting a constant in front of the linear line, 2, 3, puts it at a sharper angle, right? Well, what's going to happen if we do 4? Okay, eventually they cross right here, right? So at this point right here, we can say, what is this point? It'll tell us 3, 12. So this is our n0 from our big O equation, because at this point, our big O line, big O f of n, big O of c times n, c is 4 here, this line will always be above the black line forever, right? The black line will never catch up to it. Because we were able to find this c and a point here where they cross, we can say that this function is big O of n. Okay? We can say it is big O of n. All right, let's look at a different function. Let me grab another one and reset this. Okay? Let's do y equals big O of n squared. Okay, so this was our second algorithm for the combinations, right? This is its t of n right here. Now, the question is this guy, what is its big O of n? Right? And we're looking for functions here. N squared, 2 of n. Right? Let's say, well, are you big O of n? that implies that we can find a value for c, a constant c, where this line is going to cross over this one and the black line will never catch up. So let's go 2. C is 2. No. C is 3. No. C is 4. Well, it actually caught up briefly. Right? Y caught up briefly, but then the black line caught up again. Okay. Let's go 5. How about 5? Okay, it overtakes, but the black line overtakes again. How about 6? Right? Blue is bigger than the black line, but the black line wins again. Okay, so it's going to turn out that no matter how big we make this, right, the black line will always eventually overtake the blue line because the rate of growth of this n squared function is higher than the rate of growth of the blue line. Okay, so this blue line does not work. This n squared function, n squared plus n plus 2, our t of n equals n squared plus n plus 2, is not big O of n, right? It is not, because we cannot find a constant here that the blue line will always overtake the black line. Okay? So, but what if we change it to big O of n squared? Okay, well, if we start adding constants in here, what this does is it tightens up our parabola, right? Gets it closer to the origin. Well, if I just very simply make this constant 2, there does come a point here, right here. This is our n0, where the blue line, our f of n, crosses over our black line, our t of n, right? And the blue line is always and forever going to be bigger than the black line. Okay? So we found a constant, c, and a function, f of n, which is n squared, that will dominate our t of n line. Okay? So we can say, in fact, that this function, this is for our combs, right? Our combinations example from last time, is big O of n squared. Okay, what we care about is the magnitude of this function. Okay, big O of n squared. Right? So, when we're talking about big O functions, there's an order to them. And actually, let me, I'll come back to this. Let me go instead to this slide. Okay? So if you've got a t of n, say t of n equals 5n, there's actually a really quick and easy kind of heuristic for figuring out what its big O of f of n is. Okay, so the first thing you do is you pick the tightest bound, right? The tightest bound is, we can correctly say that t of n is big O of n to the 5th. That's correct. That is technically correct if you plot it out. We say t of n is big O of n cubed, right? This 5n is always going to be less than an n cubed line. It's also going to be less than n times log of n line. But you pick the tightest bound. You pick the thing that's closest to it. So in this case, you say t of n is big O of n. So that's rule number 1. The other thing that you do is you say ignore the constant factors, ignore the low order terms. So factor, the constant factor, that's going to be the 5 and the 5n. Just throw it away, right? We actually don't care about constants. They're fluff. We care if something's big O of 1, that's good. But if you see 5n, 16n squared, 2n, get rid of it. Those multipliers actually don't matter when it comes down to talking about rates of growth. Okay, so we say t of n is big O of n, not it's big O of 5n. Suppose you have a tn of this thing right here, n cubed plus n squared plus n log n. You throw away low order terms. So t of n is big O of n cubed, not big O of n cubed plus n squared plus n log n. Only care about the biggest term, right? So that makes it really easy to convert from t of n to f of n. You get rid of all the constant factors, the factors 5n. You would not get rid of, if the thing was just 5. You keep that because it's not a factor, it's a constant. Okay. You get rid of all the constant factors, and then you take the biggest one. Okay. Is the biggest one n? Is it log n? Is it n squared? Is it n cubed? What's the function? Okay. So here are some more examples, right? If t of n is 17, you say it is order 1. Okay, that's just kind of a rule. If t of n is a number, you say order 1. If t of n is 20n minus 4, we don't care about constant factors, right? Forget the 20. The thing that dominates here is the n, big O of n. T of n is 12n log n. We haven't seen n log n. We'll see some algorithms later that are. Plus n. Okay. N times something is going to be bigger than just n in general. So we ditch the constant factors and just zero in on the bigger term. 3n squared plus 5n minus 2. Ditch the constant factors, zero in on the biggest term. 2 to the n plus 18n squared plus 3n. You ditch the constant factors and you take the biggest term, which in this case is 2 to the n. Okay, so what's the ordering of these functions? Right, here they are. Big O of 1, that's the best. Log n, next best. We will see a log n function. Big O of n log n, these tend to be realistic. These tend to be where some algorithms fall into and you want to strive to do. Right? N squared, now you're getting into the danger zone. You get into n squared algorithms, nested loops, that's usually a bad sign. Sometimes you can't help it and you gotta have them. But when you see them, you're going to be severely limited on the amount of data you can put through a function like that. Okay. And then they get worse. N squared times log of n cubed. If you see algorithms like this, 2 to the n or n factorial or n to the n, forget it. Your computer will never finish calculating those for n's of any decent size. Okay. So you got to know this order, right? And your goal. So what's your goal? Your goal is when you're writing an algorithm, you want its big O to be somewhere around here. Right? That's your goal. You can't always do it, but avoiding unnecessary things like unnecessary nested loops will help you get here better. Okay. Now, why do we need this? Why do we care about algorithm efficiency? So the big O, this big O gives us a mathematical basis for comparing algorithm code and code efficiency. And we want to strive for algorithms that are big O of n or better. There's a way to get there. But mostly for our purposes in this class, we need to know the big O of certain operations that we do on our data structure so we can help use them more effectively, right? There are going to be trade-offs. If we're dealing with millions of lines of data entries, millions of pieces of data, how we process that data is going to have a big impact on how quickly, our operations finish. And if you're doing something like writing the code that controls a network router, for instance, the code that controls that network router needs to be fast, right? You've got billions of gigabytes of data transferring over routers. It's got to run quickly. If you're, in a hospital and you're looking up a patient's blood type in a database, that database better respond quickly if the patient's bleeding out in the emergency room. If you're in a game, right? And you've got things that are rendering all over the screen, but maybe there's things off the screen. And you got to decide, are these objects that are off the screen worth rendering or not, right? Like maybe you run past something and now it's gone, but you suddenly turn and now it should come back. How do you decide what to render, right? You can't have an algorithm that's sitting there thinking about it for very long because you'll get lag or chop in your game, right? So big O, in this way of counting how efficient your algorithms are, can help you make trade-off decisions on which algorithm to use and which data structure to use to store your data. Okay. let's just do an exercise real quickly, right? Put some actual numbers on this thing. We stress that when you're counting algorithms and you're counting the computational steps involved in code, we think about steps. We don't think about time as like stopwatch time because everybody's computer runs at a different speed. But let's put some numbers in here, all right? Let's assume for a second that a single operation on a computer, one of your constant time operations, your big O ones, suppose a constant time operation takes 1 nanosecond. Okay, that's realistic. That's a realistic assumption. Most modern computers can do 3 or 4 computations every nanosecond. So let's assume a single operation takes 1 nanosecond. If your algorithm is 2n plus 2, t of n 2n plus 2, and each operation takes 1 nanosecond, well, giving this algorithm an input of 1,000, okay, plug in n is 1,000 here, that's 2002. How much time, physical time, will it take? About 2 microseconds. That's not something you can even recognize as a human being. How about 1 billion items? Okay, it's the names of a fifth of the world's population. Okay, plug that in to your algorithm. That'll take 2 seconds. Okay. 2 seconds to process 1 billion records. I can live with that. That's actually pretty good. But now suppose you're dealing with your n squared algorithm. Okay. Again, we're assuming that a single operation takes 1 nanosecond. Plug in 1,000 things into an n squared algorithm. That's 2 milliseconds. That's not bad, but it's not great. But now plug in that billion. Well, that's going to take this long. I don't even know what this is. That's 63 years. That's never going to finish. Right? 63 years of uptime. There's probably not a lot of computers that have 63 years of uptime. And what do you care about after waiting for 63 years? Not that much, right? So this matters, right? And this is a drastic number, but 100 million, 10 million, a million, even a million in an n squared algorithm, you're going to be waiting a couple minutes, maybe a couple hours. You're going to feel that pain, right? So how you design these algorithms matters. Okay. You know what? We're going to leave off there with this. We'll get into Python lists next time, and we'll see an actual application of this. But for now, I just want you to digest, work on your homework, get used to counting algorithms, and next week we will talk about an actual data structure. Holy cow, it's the name of the course. We will talk about a data structure, and we will use this lingo, this big O lingo, to compare how different operations on that data structure perform. Right? Some of them are going to be big O of 1, some of them are going to be big O of n. And we're going to see, and we're going to demonstrate that the way that you use this data structure has an enormous impact on your program and how quickly it can solve a problem. Okay? And that'll be next week. So if you have any questions, you know how to get in touch with me, and have a great rest of your week.